This lesson here is on Newton's method, and this is a nice little technique in calculus, an application of the derivative in which you can solve equations. So most algebraic equations, you can reduce them to solving an equation where it's set equal to 0. And so Newton's method here is really a technique that you can use for finding the x-intercepts of functions. So to give you a rough idea, just informally, like how does this technique work? So we're going to imagine that we have some kind of function here. I'm just going to call it f. And the end result here, or what we're trying to do, is to pin down one of these x-intercepts. So I'm just going to focus here on one of them. And so we're really saying that this is the target, right? What we're trying to do is to figure out that x-intercept. So this method is quite different from anything that we've learned in calculus. And so the way it works here is we're going to make an educated guess as to what the x-intercept should be. And most of the time we'll naturally be wrong. So I'm going to call this over here x naught. So this is the initial guess that we make for this calculation here. You can see it's quite a distance away. And so what we're going to do in this technique is we're going to go up to the function, right, and find this location here, and then use some calculus. So we're going to draw the tangent line at this location, at this new spot right here. So this here we could call TL for tangent line. And if you look carefully at the diagram, you can see that the tangent line, if you imagine where it crosses the x-axis, is actually much closer to the intended target, the thing that we're trying to get. So the idea here is if we were to set the tangent line y value equal to 0, that would give us something that is an improvement over the initial guess that we made. So this is exactly what we're going to do. So this new location here where this crosses the x-axis is better than that. So we're going to call that x1, right? That is most certainly an improvement. And you can almost predict here that what we're going to do is repeat the process. So we're going to go right up to the curve, right, and find its corresponding y value, and then draw another tangent line. So at this new location here, put this one in here, something like this. So this is a new tangent line in green. Now you can see the place where the green line crosses the x-axis is yet an improvement on x of 1, so it's even better. So we would take this location here and call it x of 2, and then continue the process. And at some point, these values are going to get really, really close to what we're trying to achieve, and that is to figure out the x-intercept of the actual function f. So what we end up with here is a sequence of values. You have your x of 0, x of 1, x of 2, etc. And these values just march closer and closer to the intended target. So definitely this is a nice application of calculus because you can see the tangent line is involved here. So without a doubt, this formula, right, or actually incorporating this involves the derivative of this function f. So I want to take a minute here just to do a little bit of light work to give you an idea of how you develop the formula. And it is pretty straightforward stuff. So Newton's method here is all about the tangent lines. So you can just think of the equation of a basic line from algebra. And so the end that we're going to see in the diagrams, this is going to be the slope of the tangent line. So this will involve the derivative. And then your y sub 0 will just be the y value of the function. So if we rewrite this here using the information that we had in the diagram, it's not adding all that much from the top equation. So this is the y value of the function here, and then m corresponds to the slope. So if you think about what we were doing down here visually, every time you update an x value, you're actually taking the tangent line and setting y equal to 0. So that way you can calculate the x. So what we do in this tangent line right here is we're going to set this equal to 0, y is equal to 0, and then if you want to get your updated x value, it's this thing here, right, that we have to solve for. So we just have to rearrange this equation and solve for x, and that's going to allow us to solve for the next value, right, the improved x-intercept. So rather than going through all the steps, I'm just going to write down what you would get here if you solved for x, it only involves a couple of algebraic steps. So it takes on this form here. So this is what it looks like here. So if you were to solve for x, notice that it's going to involve everything that incorporates the initial guess that you made in the problem. And then you can see that this does involve the slope of the tangent line also in the problem. So once you go through and calculate this x, this is in the diagram what we call x of 1. So this here, in all theory, should be an improvement on the initial guess. And then if we use this value now in the exact same formula, it's going to give us x2, and that will be an improvement again over the x1. So what we're seeing here is we have an initial guess, x0, and then we have these improvements here. So these should get better and better in terms of accuracy, and then at some point these are going to approach the actual x-intercept that we're after in the problem. So based on this little bit of work, this is what you would find in a calculus textbook. So if you look in the book, you'll find something that they call Newton's method. And so the x sub 0 is your initial guess, right? That's how you begin this entire process. And then this is the basic formula that you're going to use for different values of n. And so when n is 0, that corresponds to the initial guess that you make, and then you end up calculating x sub 1. And you can see that the general formula that you'll find in the book is nothing more than algebra. So you take the equation of a tangent line and you solve for x, and you simply get this little iterative scheme, and this will allow you to calculate improvements on the x-intercept. So what I'd like to do here to wrap up this video is to look at an example, one that's fairly straightforward, not too difficult to do. So we'll take a look at this nice example here. So this problem is saying, let's figure out the x-intercept of this function. So in theory, what we're doing is setting y equal to 0, and we're trying to solve this equation here. 0 equals x squared minus 3. And you'll notice the example itself is a very simple one because you could solve this algebraically. And x would end up being the square root of plus or minus, or just plus or minus the square root of 3. So it could be solved by hand, but it would be interesting to see what this technique looks like if you incorporate Newton's method, because this is one where if we look at the algebra, we more or less know the answer to it already. So the only thing you need to get rolling on Newton's method is you need to start with an initial guess. And so this is something where you want to look very carefully at this equation and just say what number for x would almost make this equation true. So you could see 1 would almost work because you would end up with 1 minus 3. You could also pick 2, right? 2 squared minus 3 is almost equal to 0. So what I'm going to do here is just pick something between 1 and 2. So to get rolling on Newton's method, I'm going to choose 1.5. So there's nothing too special about the initial guess because your values, in principle, if you have a good function, should converge to the intended x-intercept. But if anyone starts with a different initial guess, naturally your calculations will look different, but the actual end result should be the same. So we're going to try to incorporate this, and let's see what it looks like. So all we need to get started, right, to use Newton's method is you need the function, and you also need its derivative. So this is pretty simple in this example. So this is equal to 2x. So now that we know what problem we're solving, I'll move this here so we have some room to write. So let's write down Newton's method for this very problem. So I'm going to repeat it here. So this is what Newton's method will look like here. And we're going to start off with the initial guess being 1.5. So we're going to use the information in our problem. We're going to start off with n equals 0, and then use all the information that we have in the actual problem itself. So this, we're going to start off with n equals 0, so x sub 1 will be x sub 0 minus, right? So we have to think of the function that we had in this problem, so we'll come back to that. Right, so the function here is x squared minus 3. So we're going to do x naught squared minus 3. And then on the bottom we have the derivative of the function. So this is going to be 2x. So this will be calculated at the initial value. So notice the right hand side of this uses all of this data from the initial guess. So what we do to calculate the improvement x sub 1 is we're going to use 1.5 everywhere in this formula here. So if you were to do this out by hand, it would look like 1.5 minus, and you just have to do some routine calculations. So 1.5 squared minus 3, and then on the bottom it would be 2 times 1.5. So I'll circle this so we can see all of this here. So once you get to this point, this becomes a calculator exercise where you're using your initial guess 1.5, you plug it into Newton's method, and then you calculate this, and it's going to give you x sub 1, right, the improvement. Alright, so if you punch all of that into a calculator, I'll let you guys try that. This ends up being 1.75. So it makes sense here that if you make an initial guess on the problem, when you calculate your first value, you're definitely going to see some movement. So 1.5 has changed to 1.75. And in theory, what this is saying is that 1.75 will better solve the equation than 1.5. So what that means is if you come back to your problem, if you put 1.75 squared minus 3, that's going to be closer to equaling 0 than 1.5 squared minus 3. So that's really all there is to Newton's method. Once you apply this technique, now we're going to take the 1.75 and update the formula. So everywhere you see a 1.5 here, we now insert 1.75, and that's going to allow you to calculate x sub 2. So I'll write it down so you can see what it looks like. So x sub 2 will be is 1.75, right, minus, and then you have to put this into the actual function itself. So 1.75 squared minus 3, right, that's the x squared minus 3, and then the derivative on the bottom, so 2 times 1.75. And what this formula will do is it will now update your x sub 1 into x sub 2, and this should become an even better approximation. So what you can probably tell at this point is that this is something that's very, very convenient to program. So once you enter this formula one time into a calculator or a computer, you can ask the calculator to simply spit out a whole bunch of the values. So x2 here, when you calculate it, it ends up being really close to the actual answer. So it's 1.732, followed by some change here, 14285 or so. So you'll notice that we had a lot of movement from 1.5 to 1.75, but now this is telling us that we're getting pretty close to the intercept. So moving from x1 to x2, there hasn't been a lot of movement, around 0.02 or so. And you can predict here that if you were to calculate x sub 3, this would be a little tedious because it would be this number here that would have to replace the 1.75, and then you would get something even closer to the x-intercept. So something that is informative here, once you understand how to calculate it and how the technique works, where you have your old value here, and then your old value evaluated at the function, old value evaluated at the derivative, then it's convenient here to list these values, right, to actually see what x1 and x2 look like all the way down the line. So this is a nice little table that is done for this very example. So you can see the initial guess where n is 0, we picked to be 1.5, and then after one calculation we got 1.75, but then if you put 1.75 into Newton's method, then you get this new value here, and that's the last one that we're seeing here. But then notice when you repeat the process, it's really this kind of behavior here, the limiting behavior, that's telling you that you're more or less stuck. And so this is a good thing because it's telling you that this is what the x-intercept is really going to be. So when you go back to this problem, right, and you think about what this means, right, go back to the original example, determine the x-intercept of this function, it would be this value here. And all that really means is 1.732 squared minus 3, that's very, very close to being equal to 0.